Right now, without thinking about it, your thumb just did something no other primate on this planet can fully replicate. That grip, thumb pad pressing against the side of your index finger, is called a precision pinch. It is the grip that lets you hold a pen, thread a needle, type a message, perform surgery. It requires the coordinated firing of at least 11 muscles, the precise geometry of 27 bones, and a motor cortex allocation that research suggests is disproportionately large compared to virtually every other body region. And none of it would exist if, 2.3 million years ago, a small-brained hominin on the East African savanna did not pick up a rock and strike it against another. Not by accident, not randomly, with intent. That act, the deliberate production of Oldowan stone tools, set off a cascade of anatomical and neurological changes that reshaped the bones in your hand, expanded your motor cortex, and drove a reorganization of your brain that researchers now believe laid the groundwork for language itself. Your hand is not a product of millions of years of random drift. It is a precision instrument that was, in a measurable and documented sense, designed by use, by a specific use, by knapping stone. This is Oldowan Gorge. In 1960, a team led by Lewis and Mary Leakey unearthed a collection of fossils here, including 22 hand bones, from a juvenile hominin that would be named Homo Habilis. Handy man. The specimen became known as Oldowan hominid 7, or OH7, and it was, from the moment of its discovery, one of the most studied sets of hand bones in human evolutionary science. Because these bones told a story about what was changing in the hand, and therefore in the brain, at precisely the moment stone tools appear in the archaeological record. Homo habilis lived between approximately 2.3 and 1.5 million years ago, across East and Southern Africa. Their brains were larger than their Australopithecine predecessors, roughly 600 to 800 cubic centimeters compared to around 450, but still less than half the volume of a modern human brain. They were small, probably bipedal, but not yet the long-striding walkers of later Homo. And they were, by the best current evidence, among the earliest members of our genus to consistently make and use stone tools. What they did with their hands during those 800,000 years produced changes in your skeleton and your brain that have never reversed. To understand what changed in your hand, you need to understand exactly what stone knapping demands of it. Oldowan toolmaking, the earliest stone tool industry associated with Homo habilis and contemporaneous hominins, required two distinct types of grip used simultaneously in each hand. The hammerstone, the rock used to strike, had to be held in a power squeeze grip. Fingers wrapped, palm engaged, substantial force generated at impact. The core stone, the rock being shaped, had to be held and repositioned with a precision pinch, adjusting the angle of the edge between every single strike. Research published in the American Journal of Physical Anthropology by Masker and colleagues, using electromyography to measure actual muscle activity during Oldowan tool production, identified two muscles as the most heavily and repeatedly recruited: the flexor pollicis longus, the deep thumb flexor that runs all the way up your forearm, and the first dorsal interosseous, which stabilizes the index finger against the thumb during pinch. Both of these muscles are substantially larger and more powerfully innervated in modern humans than in chimpanzees. Both connect directly to the precision grip capability that no other living great ape can perform with the same force and control that you used moments ago holding that pen. The key structural difference between your hand and a chimpanzee hand is not the fingers, it is the thumb. Research published in Communications Biology found that across 95 fossil and extant primates, relatively longer thumbs, the defining feature of a capable precision grip, correlate strongly with larger neocortex size. Most hominins, including Homo sapiens, have uniquely long thumbs, and that relationship is not coincidental. The data suggest brains and hands drove each other's development. Inside your motor cortex, the strip of brain tissue that generates voluntary movement, there is a region called the hand knob. It sits on the precentral gyrus and represents, in neuroimaging terms, an actual physical bulge in the surface of your brain. Research into cortical motor maps, pioneered by Wilder Penfield and extended through decades of neuroimaging, consistently shows that your hands, particularly your thumb and fingers, occupy a cortical territory that is disproportionately large relative to their physical size. The hand region in your motor cortex is not scaled to the mass of your hand. It is scaled to how much precision that hand requires, and critically, it is lateralized. Research by David Freyer of the University of Kansas, published in the Journal of Human Evolution, found striations on the teeth of a 1.8 million-year-old Homo habilis fossil that indicate right-handedness. The marks, consistent with cutting meat while holding it in the teeth with the left hand, then cutting with a stone tool in the right, represent the earliest fossil evidence for a dominant hand in the human lineage. 90% of modern humans are right-handed. Among chimpanzees, the split is roughly 50-50. That shift, from no consistent preference to a population-level dominance of the right hand, corresponds to a permanent reorganization of the left hemisphere motor cortex, expanding the neural territory dedicated to fine, controlled, sequential hand movements. And here is where the story of your hand connects to something larger than grip mechanics. Research by Dietrich Stout and Thierry Chaminade, published in Philosophical Transactions of the Royal Society B, found that stone tool production and language processing activate overlapping regions in the human brain, including the inferior frontal gyrus and ventral premotor cortex, regions that include what we now call Broca's area. Studies of Oldowan tool manufacture show that this activity predominantly engages the frontoparietal sensorimotor network and cerebellum. The neural circuitry for planning sequential hand actions and the neural circuitry for organizing sequential language are not separate systems that developed in parallel. Research suggests they grew from the same expanding substrate. This is what 2.3 million years of selection left inside your palm. The thenar eminence, that muscular mound at the base of your thumb, contains 4 muscles. 3 of them are innervated by the recurrent branch of the median nerve. All 4 exist at a size and development in modern humans that research into comparative primate anatomy suggests is a direct consequence of the sustained, high-force precision grip demands of stone tool manufacture. Electromyographic studies by Marsky and colleagues found that the intrinsic muscles of the 5th finger region and the thumb index finger region are the most frequently recruited at high force levels during Oldowan hard hammer percussion. The exact motions Homo habilis was performing 2.3 million years ago. These are the muscles that are most powerfully developed in your hand. These are the muscles that fire when you grip a pen, a steering wheel, a surgical instrument. If you are watching this on a phone, you are holding that phone with a grip whose neurological and skeletal foundations were laid before the species you belong to existed. If your channel benefits from what you learn here and you want to be in the room when the next piece of this story lands, the next video maps something equally specific about what happens to your body when you stop moving the way it was built to move. Make sure this channel is part of your regular watch list. What we cover here only makes sense when you see each piece connect. Place yourself here. You are small, 1.3 meters tall, perhaps 34 kilograms. The cognitive gap between you and the Australopithecines who came before you is real, but not vast. You have not yet discovered fire. You have no language in any form your descendants would recognize. You have a larger brain than any primate before you, but most of that volume is still dedicated to processing a dangerous and complex world. But your hands know something. You have watched this done, or perhaps discovered it through the convergence of accident and intent that paleoanthropologists now believe underlies the earliest Oldowan tool production. You select a cobble from the dry riverbed. Your fingers read its surface without instruction. The grain of the quartzite, the mass distribution, the angle of the potential flaking face. Your right hand wraps the hammerstone. The grip must be firm enough to resist the impact force that will travel back through the stone at the moment of contact, but not so rigid that your wrist cannot guide the trajectory. 11 muscles in your forearm and hand activate before the first strike. Your left hand holds the core at a precise angle, the precision pinch, thumb pad against the upper face of the stone, 2 fingers stabilizing below. The strike lands. The conchoidal fracture propagates through the stone in a controlled cone. A flake detaches, sharp, thin at its edges, useful. What you now hold in your left hand is a cutting edge that no natural process would have produced. You run your thumb pad along the edge. The nerve endings in your fingertip, the same nerve endings you use right now reading this, register the sharpness of the fracture, the regularity of the edge. Your brain's somatosensory cortex, already disproportionately mapped to your hand, processes this information faster than any other body surface. With this tool, you can access calories no earlier hominin could reliably reach. Bone marrow, meat from carcasses too fresh for your teeth to process without a blade. Resources that research suggests drove the caloric surplus underlying the brain volume expansion that defines your lineage, a lineage that eventually produces, 2.3 million years later, a species using a precision grip to hold a glowing rectangle displaying a video about their own hands. Every strike of that hammerstone was loading your ancestor's hand in a specific pattern, the flexor pollicis longus firing at high amplitude, hundreds of times per session, the first dorsal interosseous stabilizing the index finger against lateral force, the thenar muscles rotating the thumb into opposition. Each repetition was mechanical stress on bone, and bone, over generations, responds to mechanical stress by reinforcing the architecture that carries it. Research into trabecular bone architecture, the internal scaffolding inside bone, published in work analyzing human and primate hand specimens, shows that the pattern of internal strut orientation in the human thumb metacarpal reflects sustained, forceful precision grip loading. The trabecular structure adapts to load. It builds reinforcement where load is highest. Your thumb metacarpal, right now, inside your hand, carries that architectural signature. It is not just muscle and skin, it is bone shaped over 2.3 million years of consistent, repetitive, precisely patterned use. The modern hand almost never loads at the forces Oldowan napping demanded. A 2018 study in the Journal of Human Evolution, examining the manual pressures of different stone tool behaviors, noted that loading varies substantially across different stone tool tasks, with Oldowan chopping and Acheulean hand axe use placing quite different demands on the thumb and forearm muscles. The point is not that you need to nap flint. The point is that the architecture built for that load is still yours. And like all biological architecture, it responds to the demands placed on it. Research suggests that grip strength and hand function decline measurably with sedentary modern lifestyles in ways that have downstream effects on both dexterity and the neural tissue that controls it. The cortical map of your hand, the territory in your motor cortex allocated to your fingers and thumb, is use-dependent. Work by neuroscientist Álvaro Pascual León and others showed that cortical hand representations expand with practice and contract with disuse, even in adults. Your motor cortex did not stop being plastic after childhood. It is still responding to what your hand does, or stops doing, right now. Please note, the research discussed in this video is educational in nature and does not constitute medical or clinical advice. Any concerns about hand function or strength should be addressed with a qualified health professional. So what does 2.3 million-year-old stone tool use mean for the hand you use today? 3 things are worth carrying from this. First, your hand's skeletal architecture was not designed for the inputs most modern hands actually receive. The trabecular reinforcement in your thumb metacarpal, the ligamentous structure of your carpal joints, the moment arms of your intrinsic thumb muscles, these are built around the loading pattern of forceful, varied, 3-dimensional gripping. Research into hand bone density across populations with different activity patterns suggests that habitual grip-intensive work produces measurably different internal bone architecture from sedentary hand use. Second, the neural territory your motor cortex allocates to your hand is variable and use-dependent. Research into cortical plasticity consistently shows that skilled, varied hand tasks expand the motor hand map, while repetitive low-complexity tasks or disuse reduce it. This is not a feature of development only, it continues across the lifespan. Third, and perhaps most relevant, the relationship between your hand and your brain runs in both directions. Stone tool production, according to neuroimaging research by Stout and Chaminade, activates a frontoparietal network that overlaps directly with regions associated with language planning. If language co-opted the circuitry that tool manufacture built, and the evidence is accumulating that it did, then the hand is not just a tool. It is, in a very specific sense, part of the cognitive architecture that makes you human. In 1964, when Louis Leakey and colleagues formally named Homo habilis and defined it as a new species, they did something unusual. They named the species after a behavior. Habilis, handy. What they were marking was not just a classification. They were marking the moment in the human story where the hand and the brain began to build each other, where the act of making something shaped the architecture that made more complex things possible. That sequence, stone to flake, to cut, mark to calorie, to brain growth, to language, to every piece of written and spoken communication in human history, begins in the grip. Yours still holds the architecture. The next video in this series covers something that connects directly to what you just learned here. If the hand was shaped by what it was asked to do, what happens to the body when you remove the specific physical demands your biology was built around? That question has a specific, measurable answer, and it starts with something you do for 8 hours every day. The science covered here is produced because of the people who watch it consistently. If that is you, you already know what this channel is building toward.